Hello, good afternoon, everyone, and I apologize for being late. Um, okay, first I want to answer a few questions I received from email. Some of you have started thinking about final exam, which is really good. I'm happy to be asked about final exam at this time because it's still quite a long way from final. But I want to emphasize that uh, the uh, the requirement of a final exam has already been specified in the syllabus. So basically, it is just in-person exam, and it's a closed book. Unfortunately, you can bring calculator, but you cannot use any laptop, cell phone, looking for help on the internet and so on. After all, this is a regular speaking is a math class, right? We have to do some kind of like testing, though I hate test. Um, but this, but this will be just a normal test you have been gone through like numerous times. And regarding the range, I will just go through the whole what I have discussed throughout the semester, starting from the very beginning to the end, and the range will not be exceeding homework assignments. So basically, if you're super confident about your homework assignment performance, you should be fine. There won't be any issue for you. Of course, the problem won't be exactly the same as the homework assignment problems. There may be some variations for sure, but regarding level, I mean the level of the difficulty is just the same as homework problems. Question? I guess. Yeah, I'm talking about the final exam. I'm not talking about quiz. You guys are doing quiz every week, right? It's just single choice, multiple choice problems. But for the final, it's a paper exam. And everyone needs to return to the classroom. Um, Usually we don't allow cheat sheet. Um, it's uh, it's not like testing whether you understand some concept. It's like, okay, we're asking you to do some kind of like calculation, which has showing up in the homework assignments. So I would suggest that if you really worry about that, you should go through all of your homework assignments. And we'll release the homework assignment answer later, but not now. Yeah. Yeah. It will be like homework assignments. Just what? Yeah. Yeah. The same concepts. As I just said, right? We won't exceed the range of homework assignments. Yeah, it's very likely you are going to see some problem, which are some kind of like another description, another of variation of the homework problems you have seen before. So we'll highly recommend you to go over your homework assignments, and we'll provide you guys the answer key for the homework assignments for sure. But now, blast me the homework assignment key right now. I cannot give you. Any other questions? Okay, great. So, but anyway, if you feel you're okay with the homework assignments, then you should be perfect fine. And I will recommend like spend a few days then look into every problems and redo it. Or if you feel like it's so simple, just read through that, and that's all. Um, and probably that depends on the progress of our course. We will find one lecture to talking about several examples in homework assignments and make sure everyone feels comfortable. But it depends on the progress of our class. We need to make first priority that to cover all the content we intend to talk about. Another question? Oh, by the way, if you want to do some like, because if you have some like emergent schedule, you cannot join the final exam, please let me know beforehand, at least 1 week beforehand. And I will know that, but I don't have the right to schedule the time. I cannot, I mean, I actually quite flexible. If you're willing to, I can even let you to sit in my office, but this is not allowed by the university policy. So I'll have to, you need to, we need to like find some third party, I guess, some kind of administration will help you reschedule some time and the location, whichever. So please pre-allocate enough time to make it possible. Otherwise, this will be, it will be very, I mean, it might be some trouble. Okay, any other question? Okay, great. So let us continue talking about the joint probability density function, PDF, aka PDF, for continuous random variables. So we were at starting part of that definition. So a quick review. So suppose we are given two continuous random variables, x and y. Right? So we remember for a single continuous random variable x, right? So its PDF is defined based on some particular type of event. This event looks like this. Looks like this, like x belongs to some interval, right? Say belong to a and b. So we say a function f is a PDF for x if for any such type of event, meaning for arbitrary a and b, this probability of the event can be written or can be calculated from an integration of this function on this interval, over this interval. Okay? And second, we require that this function fx is non-negative everywhere. And third requirement is that, okay, if I do an integration of this function from -infinity to infinity, that means over the entire axis, right? So it will be 1, right? If you can find out a function f which satisfy these three conditions, then we call f is a probability density function for x. Okay, that's our definition. So now we want to extend to multiple variables, right? So we first extend to two variable cases, right? For two variable cases, you got one random variable x, one random variable y. So that means I'm gonna associate two events, right? One is for x, one is for y, and this event type is the same as for the single variable. A, x belongs to a and b, and y belongs to c and d. I mean, the event type is kind of the same as we define the PDF for a single random variable, but now we need to combine these two events together. So we combine them, we just look at their intersection. Namely, we want this, we want to look into the case that these two events jointly happen. Then we define the joint PDF for x and y based on this two events, the intersection of these two events. How do we define that? It's a natural extension, right? So if we can find that, so we can look at this events, right? So I can define this event as some kind of event D, right? So for this type of event D, right? Namely, X belongs to some interval, Y belongs to another interval, and they jointly, that means X and Y in this plane belongs to some rectangle, right? If we can find out a two-input, two-dimensional function f, small f here, such that for any such event D, the probability of this event can be calculated by a double integration of f. And along x dimension, it integrates from A and B. That's where x belongs to. Along y dimensional, the integration is over C and D, between C and D. So that's first requirement, right? Second requirement, we still want this f, x, and y is non-negative everywhere. And we want the double integration from minus infinity to infinity on both x-axis and y-axis is 1. Right? So we can see that this is a natural extension of the single random variable case, right? For single random variable case, you only care about one-dimensional integration, right? But now if you have two variables, if I look at their joint PDF, you're gonna look into a double integration, which integrates over both x and y. But the requirement is kind of similar in that, okay, it must be non-negative. If you integrate over the entire plane, x from minus infinity to positive infinity, y from minus infinity to positive infinity, this integration result must be 1. And third, and for arbitrary joint event, x belongs to A and B, and y belongs to C and D, the probability of this event can be exactly calculated by the double integration over this range. Any question? This is our definition. Okay. So we have talked about how do we perform double integration, right? So you can just view like step-by-step approach. Right? For example, if you start with x, right, that means you're gonna first treat y as some fixed constant. You integrate f only with x. In other words, this small f function, you view it as a single variable function, and then you do the integration over x. And after that, x disappear. The integration result is only dependent on y. That's why we can view the integration results as a function of y. Okay. And next, we're gonna do the integration again over this function of y, this capital Fy, and over the from the range C and D. And that's it. Then we take a look at a particular example, right? So suppose this is our joint probability density function, where in the range that x between 0 and 2 pi, pi over 2, and y between 0 and 1, and the PDF value is 2y times sine x. In other regions, it's simply 0. And this is our PDF. So if we want to compute the probability of a particular event that x is between 0 and pi over 4, and y is between 0 0.5 and 1, how do we compute that? Anyone? can give you guidance. Mm-hmm. Mm-hmm. Yes, exactly, right? And then you're going to integrate our PDF, right? And it's dx, dy, dx, right? You just calculate this double integration. You'll get the probability. Right? Yeah, we actually have a showing the calculation, right? At the end of last lecture, right? So this is our PDF function, right? You're gonna set the range for the integration of x from 0 to pi over 4. That's where this event specifies, right? And for the integration for y dimension is from 0.5 to 1. It's in this range, right? And then you calculate that. So we can quickly walk through that. So in the inner integration, we're gonna fix y and just integrate with x, right? So that means you treat y as constant. You just look at f as a function of x. From that, you can get the antiderivative function has the form minus 2y cosine x, right? So this can be easily verified by taking the derivative over x. You're going to recover f. And then you just evaluate the integration upper bound and lower bound, calculate difference, which will give you the result here, right? Which now x disappears because in the inner level, you have already integrated out x. So the remaining part is just the function y. And, and if you look at the antiderivative of this function, it's pretty simple because the linear function is antiderivative is square, right? So you got your antiderivative function in this form, and you just evaluate the difference of the antiderivative at the upper limit and lower limit, so you get the final results. Okay. So that's how we do this double integration. So any questions so far? Yeah, if you feel like a little bit blurred about how this is calculated, we highly suggest you to manually do this for practice. Okay, so then from the joint probability density function, we can also obtain a marginal density function for each variable. So if you want to get the PDF for x only, you can integrate your joint PDF with y. If you want to get the PDF for y only, then you just integrate out x with the joint PDF. So this is a natural extension of the discrete case, because in the discrete random variable case, you're going to sum over all possible values y can take or x can take, right? But for the continuous random variables, those random variables can take an infinite uncountable number of the values, right? So you cannot do summation. You need to do the integration. Okay. So now we want to do some example, right, to practice, right? So using the joint PDF here, right? Fxy equals to 2y sine x. I'm gonna write it here. 2y sine x, where x is between 0 and pi over 2. Y is between 0 and 1, right? Otherwise, it is 0. Right. if we want to calculate the marginal PDF for x, we need to integrate out y. That means we just integrate our joint PDF with respect to y. Does it make sense? Any question? I assume everyone is comfortable. Okay. Mhm. Yeah, yeah. Just look, our joint density actually is a function of two variables, right? X and y, right? If we want to get it a PDF for single variable x, you're gonna get rid of y, right? How do you get rid of it? Integration. That's the rule. If you want to get the PDF for y, you need to get rid of x. How do you get rid of x? Integration. Any question? This is the rule. Right? So imagine, recall that in our discrete random variable case, we just sum over y, right? Sum is integration is a natural extension of summation. Okay, so let's do some calculation, right? So here we want to get PDF for x, right? X PDF. That means we need to integrate out y from this joint PDF, right? So that means I'm gonna doing integration over y in the range 0 to 1, right? How do we do this? How do we calculate this integration? Yeah, this is the results, right? Could anyone tell how this result is obtained? Yes, exactly, right? So in this case, like if I just keep in mind, right? So if you want to integrate just one variable, that means you're going to fix all the other variables as constant. And then you just look at what is antiderivative of the function for that variable. All right, so if you look at here we're going to integrate out y, right? So that means x are constant. So the whole term like sine x is similar to the constant factor 2, right? That's just constant. Has nothing to do with y, right? So that means what you need to do is that, okay, now that it's constant, I can move it out from the integration, right? I just need to integrate the remaining terms related to y, becomes this, right? And what's the antiderivative for y? Yes, exactly, right? So for this kind of like function, if you're asked about antiderivative, you should like come out immediately. It's like you're gonna recite something very, very proficiently, right? So the antiderivative of y is just half y squared, right? And you can easily verify that using the derivative rule. You take the derivative of y, it will immediately come back to y, right? So then you just evaluate at the two ends and calculate the difference, which gives you half. Now this half and this two, they just when they multiply together, they cancel, and you have the remaining term as a result, which is sine x. Any question? Okay. Again, I mean, if you feel like you're not that familiar with that, or feel a little bit uh, blurred about how to do that, I mean, again, just practice. It's nothing special. So now let us look at another example where we want to compute the marginal distribution for y, marginal PDF for y. So now we want to look at for y. That means we need to get rid of x. Okay? We want to get rid of x. That means we're going to integrate the joint density with respect to x. So in this case, who should be treated as constant? Yes, exactly right. I'm marginalized. I'm integrating with x. That means y will be treated as constant. So that means 2y will be viewed as constant, has nothing to do with the integration, so that we can just move it out of the integration. So you only have a sine x in the integration, right? So the remaining thing is that, okay, how do we get the antiderivative of psi x? What's that? What's the antiderivative of psi x? Yes, exactly, right? So negative cosine x, and you need to evaluate at the two end, which will give you this one. And the result is 2y. Okay, any question? Okay, so next, based on the joint density, based on the marginal density, we can define a third type of the density function called conditional density. So it's kind of like in terms of the form, it's similar to conditional probability, right? But here, it represents a function, a conditional density function. It doesn't directly represent the probability for some particular type of events. It just resembles the conditional probability in the sense of form, in terms of form. So let us look at how we define this, right? So we can define the conditional probability density. For brevity, we can just call it conditional density of x conditioned on the random variable y taking value small y. This conditional density function is calculated as follows. When this marginal density of y is in the conditional part. When this marginal density of y evaluated as the small y is non-zero, then the conditional density is just the ratio between the joint density and the marginal density of the conditional variable y at the given value small y. Otherwise, it's zero. Mathematically speaking, this is reasonable, right? If your marginal density function of y at this particular value is zero, then you divide something by zero. That won't give you a reasonable number, right? That won't give you any valid number, right? So that's why we can only divide this marginal density when it is non-zero. If it is zero, we simply put it as zero. We simply put the condition that the whole condition density value as zero. Any question regarding the definition? It's very easy to, sorry. it's fairly easy to memorize the formula of the definition, right? If you want to look at the conditional density of X, conditional Y taking some value, you just divide the joint density by the marginal density of the conditional variable. And that's it. Right? Of course, to get rid of the singular case, you have to talk about whether the denominator is 0 or not. So if we take a look at the conditional probability we discussed previously, say I got two events, A and B, right? We have the conditional probability of A given B defined as the joint probability of A and B divided by the marginal probability of B happens. Right? So you see that it actually takes the same form. Right? The only difference is that the meaning different. Right? This just means okay, that's the straightforward meaning in terms of probability for some events, right? But for this guy, for the continuous random variable, it doesn't directly associate with any event. It's just a density function. Using this conditional density, we can calculate some type of the probability of for some type of events. So this event can be represented as X belongs to some range A and B, given the random variable Y takes the value small one. So we actually can use this conditional density function to calculate the probability for this type of events. How do we calculate that? Any thought? How do we calculate the probability of X belongs to A and B, given Y takes a value small y? Yeah. Well, I would say answer is close, but it's not necessarily that complex. So remember, we're talking about X belongs to a certain interval A and B, right? Does not belong to minus infinity to infinity, right? How do you calculate that? With who? With what? Yes, exactly, right? So we still do the integration from A to B, but now using this conditional density. That's it. Okay. So this one is computed by the integration of the conditional probability density with X. So you see, once you condition on something, now the type of probability associated is also conditioned on something. Any question? Okay. Yep. Formally, it is written here, right? So if we want to compute the probability for the event A is less than or equal to X and X less than or equal to B, given Y equals to Y, then that's where our conditional probability density is used. You just integrate this conditional probability density from A to B. Okay. So now let's do some practice. So this is our joint probability density, fxy equals to 2y sine x, right? We have just a method with it, right? So we have already calculated the marginal density for y by doing the integration over x, right? So remember, if you want to do the marginal probability density function, we're gonna integrate out the other variable, right? So here we want marginal of y, we're gonna integrate the x. But if you do this guy, you will give 2y, right? Which one I've already calculated. Then we can calculate the conditional probability density by dividing the joint density by the marginal density. Okay? So here the conditional variable is y. That's why in the denominator, we need to use the marginal density of y. So we see that actually the terms 2y are canceled out from both numerator and denominator, and the conditional density are just the sine of x. Any question? Okay. So similarly, we can also compute the conditional density of y given x taking some particular value. How do we calculate this? According to the definition, how do we calculate this? Uh, yeah, that's correct. But let's just use the formula step by step, right? So we first find the definition. The general definition is you divide the joint density by the marginal density. Now, the conditional part is x, right? So that means I'm going to divide the marginal density for x. So the marginal density for x, actually, we have calculated minutes ago. Here is sine x, right? The marginal density for x is sine x. So now we just do a drop-in replacement, which is sine x, right? And the joint density is 2y sine x. So you see that sine x are canceled on both the numerator and the denominator. Then we have a 2y as the result. So you see that the conditional density function for y given x taking a particular value is just the 2y. Has nothing to do with x. Any question? Okay, so let's take a rest for 5 minutes and then continue. Okay. Hello everyone. So let us start. Well, let us continue. So let's do another example to just deepen our understanding of this concept, of familiarity of this concept. Right? So here we give another joint density function, which when x and y is between 0, 1, kappa, 0, 1, in this box, right? 0, 1, 0, 1. Okay. So the joint density function value is this polynomial. Actually, it's quadratic function, x squared plus 4/3xy times y squared, and 0 otherwise. So let's try to calculate the marginal densities, the conditional densities. So let's start with the marginal density function for x. According to the definition, we need to get rid of y, right? So that means we need to integrate the joint density function with y. Okay, so means we're going to integrate the joint density function fxy with y. So we know that this joint density function will be 0 anyway if y fall out of 0, 1, right? If y is outside 0, 1, then the joint density function is always 0. So that means we can change the integration bound from minus infinity to infinity to 0, 1. Okay, so fxy dy. So then we just replace the true form of fxy, replace f with the true form, which is x squared plus 4/3xy plus y squared and dy, right? Sorry. So how do we calculate this integration? Who should be viewed as constant? Any thought? How do we do this? How do we do this integration along with y? Any suggestions? Yes, exactly. Right. You just treat x as constant. You just look at this guy as a function y. Right? You see, it's pretty simple. So x is a constant. I mean, x squared is constant. Right? So that means the first term, you just need to move x squared outside. You just do integration with a constant 1 times dy. Right? In the second, you're going to view x as constant. Of course, 4/3 are constant as well. So it's 4/3x moved outside and 0, 1 y dy. And the third term, of course, is y squared, right? And it's not constant because we're going to integrate y, this function of y. So you're going to do 0, 1 y squared dy. Any question? Okay, so what about the result for the first term? What's that? X squared times 0, 1, 1 times dy. Y is y squared, I squared y. Yeah. Okay. So the constant, what's the antiderivative for constant 1? just y, right? So that means you're gonna evaluate the antiderivative at the 2n, 0, 1, calculate difference, right? So which actually is simply 1, right? So this guy will give you a swan. How about second term? Can anyone tell how to calculate the second term? 4 over 3x. Yes, yes, exactly right. So we just need to take a look at the antiderivative of y, which is half y squared. Do you agree? If you take derivative of half y squared, it will go back to y, right? That's why we say half y squared is antiderivative of y. Then you evaluate the antiderivative at the two ends, calculate the difference, you get integration results. Right? So what's that? What's this value? What's that value? Yes, just 1/2, right? And you just substitute y for 1, calculate with this half, right? Substitute the y for 0. Oh, sorry, substitute 0 for y is 0, right? Their difference is just half, right? So this guy is half, and you multiply with 4 over 3, and you will eventually get 2 over 3 times x. Right? And third one, can anyone tell how to solve the third term? What's the antiderivative of y squared? Yes, exactly, right? We hope you are very familiar with this, right? If you're not familiar, you probably should look at the book, right? There's some table, a long table talking about all kinds of like elementary functions, what's their antiderivatives, right? So for y squared, the antiderivative is y cubed over 3. Right? You can verify that by taking the derivative. You're going to go back to y squared, right? Now you evaluate at the two end, sorry, 1 and 0, which give the result 1 over 3, right? So eventually you just combine the three results, you get the marginal density for x squared plus 2 over 3x plus 1 over 3. Okay? Question? Okay, so let's do the marginal density for y. Right? So now, which variable should we integrate out? Which variable? X, right? So just to do minus infinity, infinity of xy. Now you integrate out x to keep y, you get the density for y, right? So again, because when x outside of 0, 1, your joint density will be 0. So we just need to integrate from 0 to 1, right? And x squared plus 4 over 3 xy plus y squared times dx. What's the result? Can anyone just to give me the result without any calculation? Yes, exactly right. So this is actually you don't need to really calculate that. Of course, if you want to do, you're welcome to do that. But actually, there's a trick because you see, fxy is symmetric in x and y, right? You switch x and y, it doesn't change. That means when you marginalize x, uh, it's the same as like you replace x by y, you switch an xy, you marginalize with y. It's the same thing. So that means, okay, I'm gonna just use this result by replacing x by y. So we got y squared plus 2 over 3 y plus 1/3. Again, you're encouraged to calculate this in detail because it's a good practice. But here we just want to review some kind of trick we can leverage. Okay, so we have the marginal densities, we have the conditional density. We can use them to calculate the conditional densities. We have a joint density, sorry. Okay. So first, what is the conditional density of x given the random variable y takes some particular value, small y? How to get this form? Anyone give a hint? Yeah, use the definition. What's the definition? Mhm. Yes, 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 exactly right. So just, I mean, from the most general definition, you're gonna divide the joint density function by the marginal density function, right? Who is conditioned? Whoever is conditioned will have its marginal on the denominator, right? So y is conditional, so you're gonna place its marginal in the denominator. So the numerator is joint density. The form takes x squared plus 4 over 3 xy plus y squared. And denominator is here, right? So we got y squared plus 2 over 3y plus 1/3. And similarly, you can calculate the conditional density function of y, condition of x taking some value. Any questions so far? Yeah, we recommend everyone to manually go through this process because it will definitely be included in the homework assignments. Okay, so now we can talk about independence. So similar to discrete random variables, right? We can define the independence between discrete random variables. We also can define the independence for continuous random variables. And the definition is actually the same. If your joint density function for x and y satisfy any of these three following conditions for every x and y. This is for all x, y. Right? If the joint density function can be written as the product of the two marginal density functions, one for x, one for y, then we claim x, y are independent to each other. Or if the conditional density of x condition on y taking any value equals to the marginal density of x, or the conditional density of y conditioned on x taking any value equals to the marginal density of y. I mean, any of the three conditions are hold for every pair of xy values, then we claim the random variables x and y are independent to each other. Any question regarding the definition? Everyone's clear? Yeah, so the definition in terms of form is exactly the same as the discrete case. So now let's use this definition to check an example. So if we take a look at our joint density, we have seen before, fxy equals to, I believe is 2y sine x, right? Where x is between 0, pi over 2, and y between 0 and 1, right? So we can just move backward and say, yes, here. It's here, right? 2y sine x, x between 0 and pi over 2, y between 0 and 1. How do we check if the random variable x and y are independent to each other or not? Any thought? Then you want to add something? Yes, yes, yeah. YouTube, if your YouTube's opinions are put together, this is the answer, right? So we just look at what is the marginal density for x, what's the marginal density for y, right? And you just need to check if the joint density can be written as the marginal density of x times the marginal density for y, right? So actually we have computed the marginal densities just a while ago, right? So this guy actually is sine x, and this guy is just 2y. Okay. So if we want to look at evidence, right? We have the evidence, right? Here and here. The marginal density for y is 2y, and the marginal density, the marginal density for x. Okay, we have calculated that, but if you calculate again, it will give you sine x. Okay, so now we can verify that if you just multiply the marginal density for x and the marginal density for y, it exactly recovers the joint density for any choice of x and y pairs. So we can claim that x, y are independent to each other. Does it make sense? Any question? Okay. Of course, you can also try to look at, okay, if the conditional density function of x given y equals to anything, whether it is equal to the marginal density of x, you can check that as well. Or you can check the conditional density of y given x equals to something. It is equal or not. It is equal to or not equal to fy, right? The marginal density for y, right? You'll find they are also the same. Okay. So the next thing we want to talk about is the definition of the expectation, right? So we know that if I if we are given some probability density function for x, say, then the expectation of x, I remember we discussed about that when we introduced continuous random variables, is just an expectation, it's just an integration of x itself multiplied with the density function, right? That's our definition of the expectation for continuous random variable. So now we extend this definition to a conditional case. So we define the conditional expectation of x conditioned on the random variable y takes the value of small y as an integration of x now multiplied with the conditional probability density function of x. Condition on that, y takes the value 1. So you see that actually in what form of the expectation you get actually depends on what form of the density function you choose to integrate. Okay? If you're integrating x times the conditional density, then the result is a conditional expectation. If you integrate with a marginal density of x, then the result is the expectation, not conditionality. Any question? Okay. So we can take a look at an example, right? So if we look at our joint density function we've seen before, x squared plus 4 over 3xy plus y squared. Okay. So if we want to compute the expectation, the conditional expectation of x conditioned on y equals to half, how do we compute that? Any thought? So what do you mean by setting all the values to 1/2? Yes. And then, well, that's not complete. Yeah, remember, we need to follow the definition, right? So now we're calculating a conditional expectation, right? That means we need to get the conditional density function. Right? So here, in our case, is the conditional density function of x condition on y equals half. That means we need to calculate this conditional density function. How do we calculate that? Any thought? Yes, exactly, right? So you need to divide the joint density function of x and y and by the marginal density function y. And here, y, you're going to take the value of half, right? So that means you cannot just take the y as half in the joint density. You also need to divide it by the marginal density of y evaluated at half. And then when you get this form, you use that to integrate, multiply with x, and do the integration, you get our conditional expectation. Any question? Yes, yes, because the condition means explicitly tells you, okay, y must take y½ Okay, great. So we're gonna finish the example in the next lecture. Okay, see you on next Tuesday.